The last couple of years have been nothing short of revolutionary for technology, especially for AI. But at the center of all of this is an ML engineer stuck in the vicious cycle of constantly training, testing, and refining their models. So what if we could ease and expedite this entire experience for them? Hi everyone, I'm Upasana, a software engineer in the serverless team at Meta. And today, I'm joined by my colleagues, Shawn and Maneet, to talk more about the recent orchestration challenges in the AI space, how AI infra and serverless team partnered together to create a new workflow system, and how this new system is helping us shape the long-term vision and future of workflows at Meta. I will now hand it over to Shawn to deep dive into the orchestration challenges in the AI space.
Thanks, Upasana, for the great intro. So I'm here to first introduce how the machine learning model training looks like at Meta and why it is a complex process. So first, there are multiple steps involved in a successful model training, from pre-train steps to train to post-train. Also, the training happens at very large scale at Meta. And in this domain, things are moving fast and innovation happens frequently across all the teams in the company. And our ML engineers are dealing with end-to-end lifecycle model development from ideation to exploration to productionization every day. Hi everyone, I'm Shawn. I'm working in AI training orchestration platform at Meta. Since I started working here about 3 years ago, I know how this platform is critical to our business to be successful in AI. About 10 years ago, our earlier effort leads us to build this platform called Fblearner Flow, and it addresses a bunch of problems. For example, allow ML algorithm to be reused by many ML engineers. Also, it allows the training happens on multiple machines in a distributed manner. And at the end, it also provides a really nice UX for users to automate and manage their experiments on this platform. But there were a lot of changes happening for the past several years. For example, shifting from the CPU to GPU training, from the small scale to the super large scale training. Also, things changed fast in the past few years. The new innovations happens a lot. So that leads us to rethink whether the architecture we built 10 years ago still satisfy the latest needs and make sure we are really successful in this domain. So look at the right side of the architecture. There are two key challenges from this. The first thing is about a monolithic architecture, which leads to unclear layering of responsibilities in our platform. Secondly, is about lack of flexibility in supporting new type of job schedulers and new type of application paradigms, which slow us down in innovation. So what all these challenges leads us to? So there are three key problems we had in the old platform. First thing is about the MOEs, they have to pay high infra overhead when they want to use our platform, which leads to the slower development integration speed for them. Secondly, the integration between our platform and the Meta GPU training scheduler is hacky and unreliable. At the end, the lack of flexibility of supporting new type of job scheduler leads us to slow innovation and in some sense also prevent us from innovation. To address the challenges and the problems, what is our vision here? We want actually provide a low infra overhead while a clear layering of the key capabilities in our platform. Secondly, we want to be really flexible in adopting new job scheduler, which are there for now, and the potential new schedulers in the future. At the end, we want to support different types of ML application paradigms so that our ML engineers, they can innovate fast without being blocked by our platform. So to achieve our vision, how the new architecture should look like. In this big picture, you can see from UX to the job scheduling, all layers are now have clear separation of responsibilities and all connected via the RPC calls. And secondly, at the authoring SDK layer, now you can see we can support different flavors of SDKs so that people can author their ML applications in different paradigms. And then at the bottom, now we are very flexible in supporting different type of job schedulers, cross GPU cluster to CPU cluster to local development environment. And all this behind the scenes, we also have moved the architecture to event-driven so that our observability can be much more efficient and reliable. All this have thanks to our great partnership with Serverless team in core system, who built the MWFS orchestrator. So now I want actually hand over back to Upasana to deep dive into this orchestrator service.
Thank you, Shawn. Now, let's take a look at the 1,000-feet view of MWFS. I think this will help us create a mental model of what the system is and better understand when Maneet explains each of those AI challenges and how we solve them specifically. Here is a shard-level view of Meta Workflow Service. Each workflow is constrained to a scope of a shard. That is what helps us scale horizontally seamlessly. There are in-house mechanisms for workflow remediation, stuck workflow detection, hot shard prevention, which help us add that extra bit of reliability in the system. There's a clear separation of concerns. MWFS solely orchestrates. And whenever there is an action that needs to be delegated, it is delegated to the action service. There are events published at each stage of orchestration, which are delegated to the event router. The customers can subscribe to event router and have better observability on their workflows. The two key pieces are the node decider and the executor. The decider decides the orchestration of the graph, which workflow can run, which node can execute because its dependencies are satisfied, which node have failed and what to do next about them. The executor specializes in understanding what needs to be done for that particular node. If it has an action, do we delegate it to action service and wait for its completion? If it is a sub-workflow, do we create one and wait for its completion? And what other things can be done? At each stage, the MWFS service publishes events to the event router for better observability. All of this is described in detail in the blog post, so please check that out too. Now let's look at a workflow in action. This workflow closely resembles to an ML workflow. The decider would understand that the A node has all dependencies satisfied and would unlock it to run. A completes, succeeds, and unlocks its child nodes. This also ensures that we have strict in-order execution within the system. B would wait for the sub-workflow to complete, while C can initiate some other external runtime action. The sub-workflow completes, B is marked succeed. But what if C fails? At this stage, customers might want different behavior. Some might want to continue execution. Some may want to block the entire workflow, or some may just cancel everything downstream. In this case, the customer canceled everything downstream. We offer this kind of flexibility to steer the orchestration using failure policies, which can be defined at each node level. After E finishes, it understands that the entire workflow has finished and publishes detailed information about workflow finish, state, and why did it fail. This kind of orchestration represents approximately 85% of the workflow patterns within Meta. So if we can do this well, we are one step closer to creating a de facto workflow solution for the entire company. Now, I will transfer it to Maneet, who will deep dive into how this architecture solves each of the AI challenges that Shawn talked about earlier.
Thanks, Upasana. Let's see how we build this system piece by piece to handle the various orchestration challenges in AI space that Shawn mentioned earlier. Additionally, we will see how this overall process resulted in the architecture that Upasana just explained. I joined Meta in May 2020. Since then, I am working for a team which is responsible for providing workflow orchestration solution for various teams with wide variety of use cases. Since AI model training is orchestration problem, our team was well positioned to handle these challenges. The first challenge that we take on is supporting multiple different execution environments. Wait a minute. You might ask why we needed to support different platforms at first place. You see, AI model has steps that are very different in nature. And to execute these steps, we need varied amount of hardware and software paradigms. For instance, we need CPU-based batch jobs for data pre-processing, whereas actual GPUs are required for model training. Similarly, client hosts different thrift services for model validation and model publishing. To ensure flexibility in the system and to avoid tight coupling, we did not integrate these different execution environments directly with the orchestrator engine. Rather, we introduce a intermediate layer called action service. And action service was responsible to launch jobs with these different environments and keeping the track of the status. This flexibility helped us in optimizing many existing use cases and unlock the new ones. Let's look into one such use case as an example. We had these nodes in the system that are responsible for launching new workflow and attaching those to its parent. Previously, when orchestrator was tightly coupled with the execution environment, we have to wait to provision whole container just to run these couple of steps. But with this extra flexibility, we extracted out these steps in a single Thrift API and integrated the service with our action layer. This flexibility allows us to introduce multiple such optimization in the system, which resulted in significantly reducing the overall time to train the AI model. Let's look into how we handle the observability challenges that are faced by these different AI model trainers. AI systems need granular level observability not only for operational reasons, but for quick experimentation, course correction, and making quick iterations. For instance, ML researcher may want to look into result midway during the model run and decide if they want to continue the experiment or they should restart with new parameters. Clearly, we need detailed observability to support such challenging use cases. And this is where event router comes into the picture that Upasana mentioned while explaining the overall architecture of MWFS. Event router is a pub subsystem which continuously receive events from orchestration engine, and these events are workflow lifecycle events. Example of these events are workflow start, a node end, and if a node failed, why it failed, and so on. And on AI infra side, AI observability subscribes to these events and process them as per their requirements. Event router also allows to have multiple subscribers to the same events. This flexibility allows us to use the same approach to support various other subsystems that are needed for effective model training. Example of these subsystems are client-facing UI, AI metadata service to collect the result of various AI experiments in the past, and our logging system to support operational events. This modular architecture, where action service and event router are extracted out, helped us immensely to introduce further optimization and extend the system. Let me give you two examples, one in each category. First, talking about the optimization. Previously, when we did not have this event router support, Action Service was frequently polling these execution environments to get the status of the jobs that it has launched in past. This frequent polling was resulting in lot of wastage in compute resources. Moreover, since there is a time difference between a completion of job and when Action Service asked polled about the status of this job, this pull-based architecture was adding significant delay in overall training time of a model run. But this event router helped us in moving to push-based architecture, where these execution environments were just another publisher to event router, and orchestrator was consuming the relevant events to decide what are the next node it should enable. One thing to note here, for scalability reasons, we did not integrate orchestrator directly with the event router to consume these events. Rather, Action Service send callbacks to orchestrator engine in this approach that we have. Next, I would like to talk about system extensibility and how we ensured safe onboarding. You see, Fblearner flow is used by more than 1100 teams in Facebook. So any downtime would have resulted in significant revenue and productivity loss. To avoid this, we keep on running the production traffic in shadow mode for a long time and discovered various issues and fix those before going to production. To make it possible, we introduce a no-op/shadow service and integrate it with action layer just like any other execution environment. For technical aspects and detail about the implementation of this approach, please refer to the corresponding blog post corresponding to this talk. With that, I would like to hand it over to Upasana to talk more about MWFS architecture and its vision.
Thank you, Maneet. That was really helpful. Now I want all of us to zoom out, zoom way out, and ask the meta question. What is Meta Workflow Service? Why did we create another workflow engine? Did we not have something existing? Well, yes, a big yes to all of those questions. In fact, my peer Dan and Girish were here at the same stage talking about the different workflow systems at Meta. Over the course of a decade, we had created more than a dozen workflow systems, but most of them were tailor-made for their own specific domains, such that their orchestration, execution, and authoring was so tightly knit that it was difficult to unify, consolidate, or even reuse one for another. In fact, when we started a partnership with AI, we did not come up with MWFS overnight. We started with something existing, but very soon we realized that the new feature asks are literally retrofitting pieces into a system which is inherently not that flexible and extensible. And this made us scratch everything and go back to the drawing board, where we thought in terms of Legos, basic building blocks with discrete responsibilities such that when they come together, they create an entire ecosystem that can cater to almost all the needs of the ever-changing AI space. And this is what we are bringing back to life with MWFS. So, after the AI collaboration, MWFS has also given us a promising path forward towards progressively consolidating the different workflow systems under one umbrella in a couple of years. After the AI bit was cracked, we are now partnering with data infra, the data warehousing teams, enterprise workflows, and multiple parallel streams of investigation and exploration to club everything within MWFS. What's next for our customers? We are investing in introducing support for new primitives like loop node, MapReduce, iterator node. We believe that this will unlock way more use cases for our customers. We are investing in a drag and drop authoring model, which will help us realize our vision of creating workflows for everyone at Meta, not just for developers, but for everyone. And lastly, we are creating a UX for everything, a one-stop destination from authoring to modeling to troubleshooting, monitoring, and everything related to workflows. And this is how the partnership that started with AI Infra has culminated into something bigger, something that's shaping the long-term vision and the future of workflows at Meta. Thank you.